Hello everyone, welcome you all to the TechGig webinar. Thank you for joining the session today. The topic of today's talk is data analytics, machine learning. It will be a 1 hour session with around 40 to 45 minutes for the presentation and the remaining time for the Q&A. So if you have any questions, please send them to us using the questions tab on the GoToWebinar control panel. I am Anmol, the moderator of this session, and it gives me great pleasure to introduce you to our guest speaker, Ms. Shamsri Nandi. Shamsri owns the Data and Analytics practice for healthcare and life sciences. She has over 18 years of experience in business intelligence, big data, and data science. She has led several digital transformation engagements and has worked as customer advisory to provide strategic technology roadmaps to the organization. She has an impressive track record of introducing new data science and AI offerings, particularly in healthcare payer and pharma commercial space. So without any further delay, let me introduce you all to our guest speaker. Over to you, Shamsri.
Thank you, Anmol. Good evening, everyone. So I hope that machine learning is a whole wide subject, and I hope that we can bring in some more light in a 1 hour session, although it is a short time to discuss such a vast topic. So from the perspective of today's meeting, I'm going to follow a broad agenda of these 6 things. So I'll introduce you to the machine learning and their industry parlance, and talk about how we can design an ML system effectively. What would be the common learning methods and algorithms that is typically used in the ML context? I'll also talk about briefly on deep learning and some examples from the industry where it is widely used. Finally, we will discuss the challenges and then discuss the questions that you all may have. Okay, so let's get started. From a formal definition perspective, I'm sure many of you would have worked on machine learning, but there are three discrete aspects within machine learning. The first one is obviously supervised, and then unsupervised and reinforcement learning. So what that means is when you have the labels associated with the data, and let me demystify that. Suppose you are analyzing the likelihood of a person developing diabetes. And if you know in your data set that if your training data set or the data set on which you are fitting your model, it has the instances of those patients who did develop diabetes, that's called a label. So you do know in your training data set who has developed the disease, and it's like a Boolean it's a Boolean attribute, which is either 0 or 1. And when we use the models to fit such training data sets and train them on them and then predict other data points, that's what we call as supervised learning. Many of these statistical models are actually around that, and that's one of the aspects of machine learning. But as the systems have evolved, we have the big data ecosystem coming in. There's a lot more possibility to discover patterns which do not really need labels on them. So for example, if you are just doing clustering, if you are just identifying, say in the banking context, you are trying to find out who is likely to be delinquent, you need not always know the label. So that's what we call as unsupervised learning. The last one, reinforcement learning, is what I would call truly learning systems, and they are much differentiated in the sense that not only you may not have the label, but you may just know whether a situation is good or bad. And the whole model makes an effort to auto-identify what should be your next action. So it is somewhat like if you are playing checker, and if you know what are the good moves, but you don't quite know every single action, because if you sum up all the possible actions in a checker, it would lead you to many thousands of solutions. So reinforcement learning allows you to define actions without quite knowing them even in your training data set. So those are the three individual aspects of machine learning. Machine learning has actually evolved from AI, so I would say it's a subset of AI, but it focuses a lot on cognitive learning capabilities. It is exciting to know that the ML market is all as big as $8.81 billion supposed to be by 2022. So with that overview in mind, let's move on to some more specifics on how machine learning is being used in today's digital business. So what are why are we talking so much about machine learning today? It is because we have the ability to faster compute. We have massive parallel processing systems which allow us to do far more faster computational calculations than we used to do a decade ago. So that's a significant trend which has catapulted the whole art and science behind machine learning and deep learning. The second aspect is we have a lot more ability to analyze large data sets. So today, if you look at the way image recognition happens, it really needs plenty of space, which only say for example, NoSQL such as HBase and others could offer to you for analysis. So that's where we see a lot more relevance of these machine learning models. There's also the need to provide higher and higher accuracy. So it's not always possible to train or supervise models like it used to be a decade ago. So that's where machine learning can allow you to evolve the models over a period of time, make them more relevant to the business. And the fourth one is the ability to create autonomous learning and latent insight. So these are four themes which the digital businesses of today are leveraging extensively in various domains. I just have four verticals listed here, but then we can also talk about oil and gas and several other verticals. So coming to retail, I think that's where we have a lot of hyper personalization happening. So what I mean by that is, suppose you are going shopping and your individual persona impacts a lot about what you are going to buy, what you are going to care about if there are promotions. So a lot of hyper personalization is leveraging a combination of natural language processing, as well as a lot of data set about demographics and it takes a lot of data from the mobile handsets and previous shopping patterns. There is also conversational commerce. So as we are heading towards more and more, machine learning and deep learning technologies, it is possible to it's possible to have interactive commerce. So being able to customize the whole shopping experience when you go to a supermarket is what leads to conversational commerce. So on a certain day, say it's a rainy day, what you intend to buy on those days, it's a lot more interactive today. And obviously that leads to a future store performance and a lot of merchandising optimization and promotion personalization, as I spoke about. Coming to healthcare and life sciences, the effect of machine learning is quite impactful. And I think if you look at the way healthcare has evolved, they are typically not so early adopters like some of the other verticals like banking, but they are using it for cutting edge technologies like genome sequencing. So if some of you are familiar with the healthcare parlance, you would know that some of the times the treatments, they do not quite act in the same manner across multiple patients. So I do know of customers who are getting into real world evidence and genome sequencing, where they look at different genomic patterns and predict the potential likelihood that some treatments are going to work on the patient. So there is a lot of emphasis on treatment effectiveness and outcome analytics. There's also something called precision medicine. So precision medicine is something which is really going to help the humankind in next I would say 2 to 3 decades. And the objective is to use things like computational drug discovery and find and create personalized medicine and make it possible to even guide how much should be the titration or how much should be the medicine given to a specific individual to control the adverse effects and yet achieve a good result in terms of the treatment. So that's the there are several use cases in healthcare and life sciences. There are also image analytics. For example, you monitor tumor shrinkage in cases of oncology, and a whole bunch of different methods that you apply in the clinical setting. Coming to banking and financial services, there is a lot of emphasis on fraud analytics. And I think even though fraud analytics is something which has been done for decades and decades, but deep learning has a particular relevance in that scenario because you get to analyze a lot more data about transactions and then arrive at the potential fraud scenarios. There are also a lot of chatbots which are used, and banking is perhaps the pioneer in that. You have a lot more virtual agents to control the inflow into the customer service processes. There are also customer recommendation engine where you target a specific set of segment of customers, and of course risk management, being able to predict things like delinquency or being able to make the collections better are extremely important in the BNFS world. Manufacturing is another very exciting vertical where a lot is happening on IoT, and no better tool to use than machine learning or deep learning in the IoT settings. So some of the customers that I have worked with, I can give you some examples from that. So telematics is a huge subject in manufacturing, and the whole process of acquiring the data sets, running fuel economy and safety analytics is extremely, it's not really something which is just new. It is being done plentiful in many of the manufacturing organizations. You also have a lot of optimization of shop floors. So how do you make it more nimble? How do you control the costs, say, of inventories? How do you make it just in time? How do you optimize the assembly line? And things like that are quite common in manufacturing with the use of machine learning. There is also the concept of connected factories, and what that means is you have connected factories all the way from the point where a requisition is made to the point where where the goods are finished and the shipments are delivered. So there is a lot of focus on having sort of the factory, next gen factory, where sensors and devices are connected. At each point the relevance of predictive maintenance, so you are able to predict ahead of time which machines need maintenance, and you're also able to see in real time how different functions are processing in the manufacturing setting. So that's another huge vertical. But outside of these four, you have lots of innovation happening. I know for sure, for example, Reliance is doing a lot in the oil and gas space. So I'll just give you a real quick example. What happens is when you lay the gas pipes, I mean the petrol pipes, there are leakages in parts of the pipes which are impossible to find out because you can imagine, right? There would be thousands and millions of kilometers worth of these lines laid out all the way from the refinery to the point of distribution. So what Reliance is trying to do is to look at machine learning, deep learning, and particularly artificial neural networks to find out what are the points of failure and hence fix them ahead of time, because the leaked petrol or other components cause a lot of loss to such oil and gas companies. So there's a lot of innovation happening outside of these four verticals, and I just took these four as examples. So moving on, what does it take to design a machine learning system? So there are three key components, I would say: the task T, a performance measure P, and a training experience E. So what I mean by that is you define a target function. So you start off with a training experience where you choose direct and indirect feedback, and you experiment with novel states. So say for example, if we were doing fraud analytics, we start off by training what is likely to be a fraudulent pattern, and then we identify target function. So that target function is really the type of knowledge you want to know. So in this context, the type of knowledge I want to learn is being able to predict a fraud. So my target function would be, is the new data element likely to be fraudulent or not fraudulent? And coming to the target function, there could be several different target functions. So it is like there are many ways to get to that knowledge, and you want to know the best search strategy. So for example, it's all about hypothesis. If you hypothesize that a person who has a set of failed transactions followed by a successful transaction is probably a likely candidate, it could be your hypothesis. So in the real world, you could have several of these hypotheses lead you up to the ideal target function, which would give you the answers. So that's what we call as the target function and the ideal target function. Coming to the representation, you can have expressive representation. So what I mean by expressive representation is if you let's again consider a game. So if you are playing checker, or let's say if you're playing chess, there are several moves which are possible at any given point in time. If you listed out all of those hypotheses, each one of those hypotheses, that would make an expressive representation. But in the real world scenario, if you go for expressive representation, it's also very computationally heavy, and it is also impossible to solve the problem without overfitting. Meaning, if you overfit it into the training data set, it is likely that you are so customized to the training data set that when you get a new data element, you almost always cause an error. So that's why the objective is to move to narrow down from the expressive representation into more specific representation. We will talk about methods where it actually happens. The next step is function approximation, and the idea is that you remove the ambiguity in estimation as far as possible. So like I was telling you, there are several different hypotheses. So you define what is the best set of hypotheses, minimizing the squared error. So one of the instances of this is I think many of you would have done regression, right? So when you do linear regression, it is possible that or say logistic regression, it is possible to fit the classifier in literally infinite ways. And you as a data scientist need to identify what is the right classifier to effectively classify your data set, meaning, say that it is a fraudulent or not fraudulent. Typically, it is done through optimization techniques, and a lot of approximation is used to decide on what would be the best set of best classifiers. So just like that, in the ML context, we identify the best hypothesis to address the result that we are after. And finally, once we have created all of that, we create a performance system. So how do you measure it? It's like being able to critique it, generalize it, and then generate the new experiment. So once you have, say, arrived at the ML model, you identify how you are going to measure it. You look at your existing validation data sets, measure the error, critique it, and perhaps adjust the hypothesis and go back. And many of the times this is done automatically because we don't always need to. That's the whole point of using reinforcement learning. So now coming to more details about how machine learning happens. The first, these are different methods that you could use. The first one is a concept learning. And in concept learning, what happens is you approximate a Boolean valued function from training examples. So again, in the context of say fraud or no fraud, or in a case of a disease, diabetes or no diabetes, it's a Boolean valued function which your training dataset has. So what concept learning does is it finds the hypothesis that fits your training example. So on the right hand side, you would see here that I've listed out two hypotheses. So for example, whether or not you would go to some water sport is suppose the problem we are trying to solve. So it is a Boolean problem. So I would either go to a water sport or may not. So the hypothesis one could be that if it is sunny and there is strong wind, there is a likelihood that we would go to the water sport. And the hypothesis two is that if it were sunny, I would go to the water sport. So there are literally, if you look at these data sets, there are 6 different possibilities. I'm sorry, 5 different possibilities of different hypotheses. So it could be sunny, it could be strong wind, it could be cool temperatures, not so warm, and all of those lead up to the eventual result on whether you would go or not. So what concept learning does is it enables you to search through the hypothesis in your training example and identify which is the general and the most specific hypothesis in context. So out of H1 and H2, as you can clearly see, H1 is more general hypothesis because it has sunny and strong wind. H1 is more specific, and H2 is more generic because H2 just says that if it is sunny, we go to the water sports. So one of the methods which does this is called findus. And findus finds a maximally specific hypothesis in any given context. So as the search goes across the hypothesis, so it starts with one hypothesis, goes to the next one, and searches for the most specific one to progressively more general hypothesis, ignoring negative examples along the way. So what I mean by that is you do not consider those labels where you are not going for water sports. So you only consider the positive examples and you move across the hypothesis in what is called a specific hypothesis and more general hypothesis. So there are also other methods like candidate elimination algorithm. In the findus context, as I mentioned to you, it deduces the hypothesis based on your training data set. And it just creates it on the fly as it moves through different records in your training data set. In the candidate elimination algorithm, you find every single describable hypothesis which is relevant to your observed training example. So in this context, it could be all 5 possibilities on these question marks, if you will. And it would then be eliminated one by one, depending on the data sets that you have captured in the training. A fourth method is what you call as list then eliminate algorithm. So this is like more exhaustive, more expressive, I would say. And what you do is you do not bother about the training example. You list all the possible algorithms across the board, and you evaluate every single hypothesis and then eliminate any that you found were inconsistent with your training example. So you literally define everything that is possible. You do not bother about which one of these is likely not contained in the training data set. You eliminate it later on when you find there is an inconsistency, otherwise you retain it. So for example, if your training data set did not have any notion about the temperature of that day, you would still keep it because there's no inconsistency. If there were an inconsistency, you would remove the corresponding hypothesis. So what is biased and unbiased? Biased hypothesis space is when you only have conjunctive hypothesis. So in this case, what am I doing? I'm only looking for those instances where I have a positive label. So where I know that the person is going for water sports. So it is a biased hypothesis space because I've only considered conjunctive hypothesis. I've only considered those that impact the solution positively and not negatively. I've literally flipped through and glossed over all negative hypotheses along the way. So that's called bias. And you could call it an inductive bias. So you induced bias in the whole solution by ignoring the negative outcomes. An unbiased learner is basically a learner, a solution where you've considered every teachable concept. So theoretically, you considered each and every hypothesis that was possible regardless of your training data set. The problem with that is that you have a lot of you do have an unbiased algorithm, but there is a lot of computational heavy process you would do along the way. So that's what we call as unbiased learner. So I can see there are some questions. So Anmol, should we take the questions towards the end?
Yeah, we'll take the questions towards the end.
Okay, perfect. So please keep writing your questions. We will just go over that for the last 20 minutes. So I'll move on to the next algorithm, which is quite well known. I'm sure many of you are familiar with decision trees. So in the interest of time, I'll go over this subject really quickly. So what we do is in a decision tree, this is a funny example. So say, am I hungry? You start from the root and you go to the bottom, so to the leaf node. And one of the most, this is a very practical method for doing inductive inference. So you induct the inference. The decision tree is actually represent a combination. It represents a disjunction of conjunctions. So what I mean by that is that you have the conjunction is your yes path, right? So where your outcomes have been yes. So for each leaf node, you have both aspects. So go to the restaurant is a positive outcome of whether I have $25. And go to sleep is when I'm not hungry, so I don't need to eat. So each path from the root to the leaf corresponds to a conjunction. So all of these are conjunctions, but the tree itself is a disjunction of the conjunctions because you have sort of eliminated and considered the negative outcomes at a tree level. This is called a greedy algorithm. Why is it called a greedy algorithm? Your objective at every single point is to go for the highest information gain, and what you're trying to find out is you are trying to select the best attribute that helps you classify the data. So these are called greedy algorithms. And what are the challenges of decision trees? Typically, it leads to a lot of overfitting. So if you had to practically create a decision tree all the way down for every single data you had in your training data set, it's quite likely that you would make it so specific that it would be hard to implement for other problems. So how do we get rid of overfitting? There is something which we call pruning the decision tree. So let's say I may not necessarily buy a burger, right? It's just that the training data set had it that if I do not have $25, I would likely buy a burger. But it's quite possible you get pizzas for less than $25. So in such cases, this is really overfitting. And what we could do is to drop a subtree within the decision tree, and that's what you call as pruning. So there is plenty to talk about, but in the interest of time, I will skip this because most people do have a fair understanding of decision trees. I just want to call out some typical scenarios where decision trees do a great job. And some of those are related to training data sets which contain error. So it's quite effective to spot those errors, and it's very robust to some sort of error handling within your training data set. It's also more relevant to target function with discrete output values. Now that's a big one. if you look at this tree, each of those questions are discrete. Am I hungry? Yes, no. Do I have a certain dollars? Yes, no. All of these are discrete values and not continuous. So where they start having problem is when you have continuous data. If instead of saying, have I got $25, if the question was, how many dollars do I have? Is it a 5, 10, 16? Then you could possibly say, buy a burger. So that's where decision trees start having problem due to continuous data sets. So we'll move on to the artificial neural networks. This is what we call as biologically inspired. That's just how we think. So in our minds, if you are looking at say if you are looking at a speeding car, your ability to perceive in your mind that the speeding car might or might not meet an accident goes much far beyond just a simple interpretation of the sensory data that is coming through your eyes. It is a combination, it is a complex real world problem which goes across several different layers of intermediate thinking. And that's what artificial neural networks is truly inspired about. So what happens is, it is an approach, again, it's an approximation approach. And what we do is we interpret the real world sensor data by going through a set of inputs, a summative function, and an activation function. So let me try to demystify it. Now let's consider x1, x2, x3. All these are your features, right? So these are things you know about something. And the W is the weights. So what I mean by that is, initially the weights assigned are random. When you start implementing a artificial neural network, all of the weights would be random, but you evolve them over a period of time, and that's why it is called. That's why it's a system of learning. So what happens is that you go over different parameters, and you try to find out if the weight was right or not. So in the context of a speeding car, it's not just about the speed, but maybe the driver's driving pattern. If the driver is driving in one single lane, likely that there may not be any accident. So what you do is, initially you assign random weights to all these possibilities, and then you sum them up, and then you sort of create an activation function where you finally decide on what the output is. So the activation function could be quadratic, it could be linear, it could be quadratic. And what happens is, you over a period of time, every time you have the activation function and you arrive at an output, you find out how close or how far are you from the real results. And that's where you try to minimize the error, and then you revise the weight, and then you say, you know what, speed is not the only predictor for accident. So I will assign less weightage to speed, and I will potentially assign more weightage to the driver's lane behavior. But see, this is a very primitive example I've given you. In the real world, in the context of image identification, it's far more complicated. And one of the methods which is used in backpropagation is backpropagation in ANN. This is called a parameterized system of learning, because you are parameterizing the weights essentially. And the key components of ANN are the perceptron, which is, it takes a vector of inputs, and it calculates a linear combination of this input, somewhat like the diagram that is shown at the bottom of the slide. And the other components are that you have the weighted inputs, which we just spoke about. You have the transfer functions, and you have one single output coming out from this. So this is how ANN is typically done. The backpropagation method searches across all of the possible hypotheses like we discussed last time, and it iteratively reduces the error. So as I mentioned, as you go along, the ANN models become better and better. So and the key thing is, it discovers intermediate features, just like the way you think in your mind. So if you look at say I don't have that picture here, but just visualize this. If you have a muffin, with chocolate chip cookies on it, chocolate chips on it, and if they were equally distributed, just like the eye of a dog, and I think you will find these images on the net if you want to look at, and then you have another, you have two at the top and one placed in the middle. Literally, it may appear to you like a muffins to the computer. So that's exactly how we think. So we have many intermediate features. So we look at not just the placement of those chocolate chips, but we also look at the texture of the muffin, and we say that, you know what, this is a muffin and not a dog. So on the lighter side, but that's how ANN evolves over a period of time. I'll quickly move to the Bayesian learning system. So what happens is you have the training example, and it's a theory of probabilities. So you know the prior probabilities, and based on that, you decide each of the candidate hypotheses. So given something happened, what is the likelihood of another event to happen? So that's where the third bullet point, you have posterior probability to each candidate hypothesis, and based on that, you assume, you look at the priors and the observed data, and you arrive at a knowledge. So new instances are basically classified by combining your collective knowledge from all of the previous probabilities, and the prior probabilities of each candidate hypothesis are used, and then you use the probability distribution to come up with the final outcome. So one of the examples is the sensor-based context awareness of mobile computing. So what it means is, suppose I'm browsing on my mobile. So let's say I'm playing music. In all of your mobiles, you have the volume up down buttons, right? So knowing when I am changing the ringtone volume vis-a-vis when I'm changing the volume of the music is entirely based on the context, the screen open on my mobile and the audio which is playing. So if there's an audio playing, I'm likely talking about increasing the volume of the mobile device and not of the ringtone. So that's where Bayesian learning comes into being. You can look at prior probabilities, and then you can identify what is the next probability likely to be. Naive Bayesian, however, is a different model, and a different model in the sense that it does not consider previous prior probabilities. It believes that everything right now is just a function of the probabilities at this moment. It does not depend on what happened before. So now coming to some of the other instance-based learning mechanisms in machine learning, k-nearest neighbor, another widely used algorithm in the industry, and a lot of you might have potentially implemented it, is when you identify the nearest neighbors to a new data point, and you locally you assign a method, you assign whether or not to classify it. So in this context, you have the blue points and you have the red points. So by virtue of having three red points, if we know that the new element is likely to be a zero outcome value, I could probably cluster or segment it that way. But in this context, for example, there are two red neighbors and one blue neighbor. So the decision becomes slightly fuzzy, and k is equal to 3 is the number of neighbors you are considering. And the challenge is that all computation is performed at the classification time. So all of this is happening when you are doing the classification. So that's one of the challenges of the nearest neighbor. There's another method under instance-based learning, and it's called the locally weighted regression. So it is really a generalization of the k-nearest neighbor. And what you do is you use the distance weighted training example. So for example, you not only see who is nearby, you also see the distance with the nearby points. So for example, this blue point is close to this one and this one and this one, right? So these are the three nearest neighbors, but this neighbor is very far. So you create a distance weighted method of finding out what would be the outcome you would like to map with. And in this context, the target function has to be approximated to some sort of, actually the target function, right, like we discussed earlier, is could be many target functions. So it is approximated through either a linear, quadratic, or a multi-layer neural network. Sorry for the typo. That should be neural network. Um, right, so let's now look at reinforcement learning. Anmol, I'll just take 2-3 minutes to wrap up and then we'll go over the questions. So the reinforcement learning is when the training information is not known. That's truly like human thinking. So I've got these funny emojis on the right hand side. Let me tell you what it means. So if it were fire and the weather outside was cold, possibly being closer to the fire would be a good, happy feeling. It would be a feeling of warmth and comfort. If you were, so we give it a positive outcome, okay? If you were close to the fire, so close enough, and you know the person's hand is so close to the fire that it got burnt, we know it is an unhappy feeling. It is very simple in our mind's eye. We know it instantaneously because we already have the learning systems established biologically. But when you have to train a computer, you have to know the training information somehow. But that's the whole aspect of reinforcement learning, that you do not have the training information. You do not know what leads to this happy feeling and to the sad feeling. So that's what we call as reinforcement learning, where you define on the fly that being close to the fire in a cold weather is good, but being too close leads to unhappy outcomes. So if you see this, you are at a state ST, there is a reward RT. These are the rewards basically. The +1 and the -1 are the rewards, and this is the environment. So the environment, if it is a good, if the outcome was good, there's a positive reward. Otherwise, there's a negative reward. And based on a combination of those rewards, the agent learns on the later point in time that which action is the right action. So that's what we call, this is the autonomous agent which senses. So this is the sensing agent, and it acts in the environment to learn what is the optimal action to be taken. Many of the methods are used to make it happen. Reinforcement learning is still very much widely in use, but such things have existed from time immemorial, and Markov decision processing is one of the methods where we apply the state transition probabilities and identify the actions or states which are likely to be. Q-learning is another method where the agent learns an evaluation function and states and actions. So that's what is reinforcement learning in a nutshell. And lastly, let's just look at few examples in the deep learning world. So deep learning is nothing but a neural network with many, many layers in between. So if you remember that input and output example, deep learning is all of these intermediate layers that you have in between each of the non-output layers. So these green ones are non-output layers, is forced to learn the good features from the previous layer. So in that speeding car example, if there is a speeding car, your next learning is it in the right lane? And your next one could be whether he follows signals. So each of the layers learns from the previous layers, and you have a very deep learning. So that was a very simplistic example. In the context of medicine and biology, this is far-reaching. So for every genome, there are millions of possibilities of how a disease will progress, or how an outcome will look like for a treatment. So what we do is we go over the complete set of outcomes and make the tree deeper and deeper. And that's where you have an evolving machine learning model. So these are some of the use cases where we've seen deep learning used a lot: image classification, speech recognition, in media and entertainment, doing video searches, for example, like the YouTube searches that you have, security, being able to look at features, facial features, detect them, surveillance, and I can't quite remember the name of the autonomous machine, but there is a machine which is which is using a whole bunch of deep learning to get to the point. So that's pretty much it for today's session, Anmol. I don't think we had time for the poll, so let's go over the questions.
Thank you, Shamsri. The questions are displaying in the questions panel. You may take up the questions.
Sure. So let me make an attempt to take as many as possible. So what's the trade-off between the bias and the variable? Yeah, good question. So Prince, the trade-off between bias and variable is that theoretically you could consider every single thing, every single concept along the way, but you don't want to do that because computationally there is a trade-off, and it also makes your model far more complex and sometimes overfitted. So the trade-off between the bias and variable is you arrive at the most optimal solution without really going into the the whole test of every single hypothesis. Practically, it is only possible over time. If you did something like concept learning, it is not quite easy to run through every hypothesis. The next question I have is Sumant, you are working on a Java project. Does it make sense to? Yeah, of course, why not? I mean, machine learning is a growing subject where there is a lot of relevance. So of course, Sumant, you could pick up many courses on several different sites, and there's a lot of learning knowledge available. By the way, for the benefit of you all, I'm not sure if you know, but machine learning has existed from as far ago as 1959. So it's not a new science, but you have plenty of resources to study it now. Is reinforcement model better for chess than supervised and unsupervised model? Good question. So reinforcement model actually, I would say, is better for chess in the sense that if you had to implement it, you wouldn't possibly know all of the outcomes. So practically what you have to do is to define each of the combination of the matrix of the chess, right? So you need to know every single combination of the possible moves to say what works and what does not, and that's a difficult thing to do. So I would say reinforcement model, or not just reinforcement model, it could even be artificial neural networks. You go over move to move and you develop a better understanding. But yeah, more specifically in the reinforcement model context, when it is a checkmate, right? So a checkmate could be a reward with a negative reward, and if you won it, it would be a positive reward. So absolutely, that's a use case for chess, no doubt. How ML is useful for farming, and what will be the basic cost to implement it? So I'm not too sure about which type of farming in context, but yeah, so machine learning is definitely useful. And coming to the cost, you have most of these are open source tools. There are plenty of those. If you look at even Google's TensorFlow, it is extremely exhaustive. And I think even if you look at the Python libraries that you have for machine learning, they are very exhaustive, and you could do a fair job in your business setting if you wanted to implement it. I don't think it costs a lot. What costs is how you train and optimize the model. The next question is, do all machine learning algorithm contain bias? If yes, how can we remove it? So Hamid, most of the algorithms would contain some amount of bias because it is like the inductive bias. What we are doing, Hamid, is we are converting an inductive system into a deductive system. So not to lose you in the jargons, but what I mean is you have a set of known situations. So that's your inductive data set. It trains you as a machine learning model. It trains what should be the behavior of the model, and you convert it to computationally implement it. You convert it to a deductive model. You say that, if XYZ happens, this is the outcome. So by virtue of moving from an inductive to a deductive model, you've already introduced a bias because you did not consider all possible methods to get there. So how do we remove bias? One of the methods, the rudimentary methods, is that you basically keep on looking at a holistic training data set, a training data set which has the maximum possible hypothesis which you are after, or from where your target function is borrowed. But again, that comes with its own trade-off, like I discussed last in one of the questions before. So the other way of removing bias is when you change the model and you do something like a deep learning, where you are creating more intermediate states in between, or you are using reinforcement learning, where you do not know all of the actions up front and you are learning in the process. But that said, there will be some bias in most of the scenarios, and the ideal thing to do is to measure your squared errors and make sure that you are as far close to that, or you improve it over time. Arundhati asks, I'm very new to machine learning, how to start? Okay, so Arundhati, there are plenty of resources, like I mentioned. You may want to go to edX, Pluralsight, and Coursera. They give you wealth of different machine learning courses. I would say in today's day and age, the best part is that you have so many extremely good software available that I don't think you had any of those a decade or two before, when it was just SAS, which used to be SAS and SPSS, which used to lead the market. So I would say, on a lighter note, just make a beginning. The next question is, could you please share some good scenarios of ML implementation for revenue cycle management in healthcare? Okay, yeah, so being from healthcare, I quite like that question. So what is revenue cycle management, for the benefit of everybody on the call? It is like, say you are a healthcare provider or a hospital, right? There is a lot of austerity measure in US, and that leads to a control on healthcare costs. So the revenue cycle is really about the cost incurred and the profitability of the providers, and being able to provide the same quality of care at a minimal cost. So that's in a 30,000 feet view of what is revenue cycle management. So coming to your question, Arif, it is the good scenario of machine learning could be that you look at outcomes, because you will agree with me, Arif, that if the outcomes of your treatment are effective enough, the provider is effective. In the US, they get a better rating for good outcomes. If the outcome is not good, both the provider and payer, that is the insurer, they spend a lot of money to solve those. So I would say machine learning is very suitable for deducing clinical outcomes, like the way, say, if somebody has a lung cancer, how to improve their probability of leading a better life, not ending up in emergency all the time. So it actually ties into a whole bunch of clinical genomic analysis and identifying what treatment is right for him, what level of chemo can work on him. So all of this, I would say, in my mind, clinical outcome is a great use case for machine learning, and I have spoken to a few customers who thoroughly believe that. Two questions from Akash. Are simple machine learning algorithms being used these days, as this is deep learning area? Okay, can we use neural network for regression and clustering too? Yeah. So the first question, Akash. Machine learning, of course, is deep learning is fast catching up, but that does not rule out any of the simple machine learning algorithms in my mind. I've still seen a broad usage of supervised and unsupervised models, I would say, more than even deep learning, because deep learning may not be suitable or maybe an overkill in some of the scenarios, like the question just before, right, on revenue cycle management. While clinical outcomes can give you great results with it, but if you implemented deep learning in the context of that, that would be an overkill. So I would say the algorithms are as relevant, and believe me, all these algorithms have literally existed from the 60s. They are still relevant today. That said, deep learning is particularly suitable when you have a huge data set. So I would say it's not like a universal thing, it's very subjective, and you might want to use it in your businesses depending on the use case. Coming to your second question, which is whether neural network can be used for regression and clustering too. Yes, so in neural network, you can use all of the different models as part of your inductive step to do it. So that's absolutely possible. The next question is minimum number of records and parameters useful for ML model. No, okay, so there is no minimum, if you will, Dhiren. It depends a lot on the outcome that you are trying to achieve. Sometimes what you need to look for is your training data set should be a good representation. It should have most of the hypotheses which are going to be commonly part of your machine learning outcome. But it could be scenarios where you have the machine learning model and say you have many different features in it. So if you have more number of features, ideally, I mean this is just a rule of thumb, you would need much more records in your training data sets. That's because if you had a large set of features and if you had a small set of records, most likely you will overfit. So I would say it's subjective, and some of the models require more records than others. But I would say, for example, even if you look at logistic, right, it requires a lot more records for a good classification. Yeah, but there's no single rule, like how many records should be present. By the way, I have seen statistical analysis done on even 60 records, so it depends. I'll give you an example, by the way. If you have 24 months of record of the share patterns or the returns on a specific portfolio, you can still go ahead and implement machine learning. Next question from Neer is, sometimes I compare ML to astrology. Okay, that's a good thought. In sense, they both try to give predictions. My question is, in real world, what is the guesstimated or estimated percentage where predictive analytics does give good probable result if it had been matured, then stock market would have been conquered? Oh, I completely agree with you, Neil. Definitely, I wish there was such a magic wand in a deep learning environment where you could predict the stock value, and then we all would have been the richest people in the world. But that said, I quite like, I can't remember the name of the statistician, but he said that all models are wrong. Some models are useful. I hope that answers your question. The next question from Mrityunjay is, statistics and data are all about probability. What is the percentage success rate of AI machine learning at an industry level? Mrityunjay, that varies a lot across the board, but I'll just try to quote some statistics with a few customers that I spoke to. For example, if you look at healthcare and if we talk about diabetes rate prediction, that's a lot to do with a probabilistic score, because if you can imagine, a false positive means falsely calling a person for wellness scoring, and hence wasting money which may not be required. So I have seen success rate of about 80 to 86% in some of the Blue Cross customers in the US, but it's the success rate is quite, I would say, is less evolved in some of the newer models. So initially, if you implement deep learning, your success rate might be quite low, but it improves over time. What is the simplest this is the next question. What is the simplest ML model to implement for a new learner? Everything is simple, I would say. You could probably try with some of the clustering techniques. You could try with the nearest neighbors. They're pretty straightforward to understand, even if you are looking at the algorithms, and they do a decent job. Amit asks, Bayesian learning, can you please give me example so that I can okay, Bayesian learning is really about probabilities. So say, for example, you are you are estimating the probability of it raining on a certain day, and let's say it is right now the rainy season, say it is exactly the same month in Pune. So what could happen is, if you are it may be dependent partly on the humidity levels of yesterday. So the Bayesian learning really considers a conditional probability that it will rain today if some of the other things hold good, is probabilistic, right? So I would say that those examples where you have a conditional probability and you have a sum total of probability today, as opposed to a year before, or a month before, or a day before. So what I mean to say is, when you know the past probability and you are estimating the future probability, that's where Bayesian learning can be quite helpful. In the interest of time, I will be real quick. Is there any prediction algorithm other than naive Bayes which gives better optimization solution? Yeah, so Vikram, there are lots of models that we spoke about, and naive Bayes is probably one of the naive models. There is a lot more depth in many of the other models. So I think we ran out of time. Anmol, can we spend 5 more minutes?
Sure, sure.
Okay, so how hierarchical clustering is different from local weight regression. So hierarchical clustering is, you will probably cluster and you will follow the hierarchy. You may not necessarily assign the weights. So for the local weight regression, you would have the weights assigned, and you are going to parameterize and adjust the weights for the local regression. So I would say that clustering, by the way, would be more unsupervised, right? Because you need not know the label, but in the context of regression, you do know the label, but you are essentially adjusting the weight. So that, I would say, is different. Hamid asks, what is the most complex AML algorithm at present? Actually, most of those are complex because you have to get a fair accuracy. But from an implementation standpoint, some of the ML algorithms are difficult to implement. Contrary to popular belief, ANN could be quite simple to implement at first, but difficult to train on the, as we go along. Which ML algorithms should know if someone wants to become a good data scientist? It is not about the algorithm. I would say, as long as you know the core statistical nuance, you should be, your first target should be to know that, and then with the tools and algorithms. Navanita asks, where reinforcement learning is used in real world. Good question. So reinforcement learning is used in the context of those scenarios where you do not quite know the outcome, so it is not anticipated. In the healthcare scenario, I can tell you that it's used in real world evidence. So real world evidence is, you make a guess whether a person whether a person is a good subject for a clinical trial, and if that person is likely to have an adverse event. So a whole bunch of signal detection and a lot of deduction on their past medical history, diagnosis history, can lead you to a target state action, an ideal action that you would like to take. And reinforcement learning is also used widely in these cars. I mean, those cars where you have to decide on the fly, you don't quite know what will happen. Or even in image analytics, just imagine a CCTV camera, the front of the, the images which are in the front, you don't know what are on the side properly and on the back. So that's also an example of reinforcement learning. Akash says, what's your take on deep learning replacing traditional ML algorithms? So I don't think that any of these algorithms are replacing each other. They are very context sensitive, and it depends on the use case that you have at hand. I'm sorry, we have to go over quickly. We are working on a project, early forecasting of disease. Okay, which probabilistic model will be better to predict possibility of disease by analyzing output from image processing? So I think there are several different algorithms. It's no one algorithm can help you get there, but I think you could do a fair job with even Markov decision process, where you have a similar journey of another patient, and then you compare the images and you arrive at a conclusion. Just a thought, but there could be several other examples. How ANN is applied in the reliance example you mentioned. So yeah, so artificial neural networks allow you to create and deep learning allows you to create several layers in between an intermediate insight about, say, a leakage, a hole being done, or the hole not yet but may happen in future. So that's where ANN can play a role. I think we have exceeded all of the time, so sorry for the questions I could not address. And more over to you.
Thank you so much, Shamshri, for this really empowering and motivating session today. And I would also like to thank all our participants for making this webinar a great success. This session has been recorded and the recording will soon be available on techgeek.com. Thank you everyone for joining us. A very thank you to you, Shamshri.
Thank you. Thanks, Anmol, for organizing this. Thank you so much to all the participants.